Okay, this one. So do this one, the derivative of this function here, which you can also write it like this. So what is the derivative of this? So again, it's just use A, B, C, and D. Okay, anybody need more time? Okay. Okay, let's see, what was the answer? Which is the right answer, A, B, C, or D? D. Okay, so you do know what you're doing. You just didn't recognize this rule, but you're using it anyway. So, yeah, it's D, right? This one. Because why is it? Because we start with this. What do we have to do first? The derivative of the outside function. That's what this means. The outside function G. The derivative of G. So the derivative of the outside function is 1/2. This to the negative 1/2. So that's here's the 1/2 here, the 2, and the negative 1/2 is here. Raising something to the negative 1/2 means the square root of it in the denominator. And then the derivative of the inside, that's here. Here's the inside function is h, the derivative of h. So the derivative of the inside, which is this part here, the derivative of that. So that's 3x squared minus 2. Okay, let's do another one. Okay, let's do this one. Okay, let's try this one. So the chain rule for this function here. Whoops, I gave it away. I told you need the chain rule. Okay. So again, A, B, C, or D. What? Sorry? Oh, yeah. X to the third one. there's the function, x, e to the x cubed minus 3. And there are the answers. Okay, anybody need more time? Okay, so let's finish that one. Okay, so which is it? A, B, C, or D? Which one? C. Yeah. Good. So we have to take the outside function is which function here? What? The outside function is e, right? E to the something, right? So we take the derivative of e to the something, we get what? E to the something. So we still get this part here. And then we have to take the derivative of the inside, which is this part up here, derivative of that. And we have to multiply it times the other result. So this is the derivative of that blue is 3x squared. So we have to multiply 3x squared. Right? Everyone agree? Okay, good. Okay, now this one is kind of tricky. What is this one? What is f? So f is not just, like in the first problem, f was equal to g of h, right? A composition of two functions, right? But what about in this example? Now f is what? Composition of three functions, right? So what do we have to do then if we want the derivative of f with respect to the inside variable? Okay, do you understand the question? Okay, so it's going to be one of these formulas, it's going to be some formula. And you can work it out because you just do the chain rule and then you're going to find you need to do the chain rule again. So you're going to do it, you're going to be forced to do the chain rule twice. So I'm not going to do it, but you're going to be forced to use the chain rule twice. So it's going to be the derivative of the outside function evaluated at the inside function. So that tells me it's going to have f prime of the inside, but then it's going to be the derivative of the inside function, right? But what are we going to have to do when we talk about the derivative of the inside function? We're going to need the chain rule again for this one, because this is still two functions, right? A composition of two functions. So we're going to need the chain rule again to get that. So what is it going to be? It's going to be y prime of x of t times the derivative of the inside function. So actually it turned out to be the first one, a. Okay? But that's how you see it. Okay, so this is like the triple composition rule, right? So the derivative of f with respect to the inner variable, which is t. So you have to go, you have to do just what we said. You have to take the derivative of the outside function with respect to this is the inside function. Okay, but then that's this part here, but then you need the derivative of the inside function, but that's really two functions, a composition of two functions. So that means you have to do the chain rule on this part as well. So then you get y prime of the inside function times the derivative of the inside function. Okay? Okay. All right. Now for next week, more fun, I want you to do this course. Now, unfortunately, we won't get to do the good part of this course because we don't have time. But what I mean by the good part is from the second week of this course. So this course is the preceding course in this series. So it's by the same guys. It's still by Imperial College London, and it's the same, this guy, well, I don't know, this guy wasn't in the first one or not, I forget. This guy, and this guy. So it's by the same people. And we did, what was it called? This one was called, what was it called? Multivariate calculus. We did the first week of that. Now, really, to go to the second week of that, we should really do the previous course in this series, which is here. So this is called Mathematics Still for Machine Learning, but this is the course called Linear Algebra. And this course has how many weeks? Week 1 has 5 weeks. But from the second week it gets interesting, but we don't have time to do that, so we're just going to do the first week, which is, there's not too much there, I guess. Just a quick discussion of vectors and operations on vectors. Okay, this next week gets into some fun stuff, but you'll have to do that some other time. Okay, so for next week we'll have a quiz on this one. So if you, for example, if you wanted to go to week 2 of the multivariate calculus one, it would be good if you first went through this linear algebra one. Then you can go to the second week of the multivariate calculus, and you'll see a lot of interesting stuff happen in week 2 and week 3 of the multivariate calculus. And this linear algebra course is a great course, but you'll have to do that some other time. Okay, any questions about the homework for next week? So the homework is for this class here, linear algebra, and we're going to do week 1. Okay, we'll have a quiz on that. Okay. All right, so we were talking last week about integrals. And we saw this notation last week. We got introduced to this notation, right? Okay, so I told you that this was like a very weird notation for something that's not so hard, right? This is really the antiderivative, right? Remember that. So what we're looking for is the function whose derivative is this. Okay, let's take an easier one if they have one. Okay, this one. Suppose I want the function whose derivative is x to the 4th. So can you think of the function whose derivative is x to the 4th? So something tells me that it has to be some kind of x to the 5th function, right? Because if you take the derivative of x to the 5th, you get x to the 4th. But if you just do the derivative of x to the 5th, you don't get just x to the 4th. What do you get when you take the derivative of x to the 5th? What do you get? 5x to the 4th. So we get this extra 5 in there, which isn't in here. Right? So we can't say that the function whose derivative is x to the 4th, we can't say that is x to the 5th. That's not quite right. Right? But it's close, right? Getting close. So can we fix it? What can we say? Which function has derivative x to the 4th? It's going to be something like x to the 5th, but not exactly that, right? So what is it? Right, so it's, if you take x to the 5th, we're going to use that, but we're going to put a 5 in the denominator. So that will cancel out when we take its derivative, the 5 that we get multiplying, right? So if we do x, so he said x to the 5th over 5, right? Okay, everyone see that? Okay, so what did we just say? The antiderivative of x to the 4th is whatever we just said, x to the 5th over 5, right? Okay, so we just reviewed this concept of antiderivative, okay? And this symbol is just a symbol, a kind of crazy symbol for that. So the answer to this is x to the 5th over 5. The answer to this problem is x to the 5th over 5, because it's just a symbol for that question. Okay? Okay, so then you can go and try and figure out this one. How about this one? Okay, kind of tricky. What is it? So the rule was that we raise this to the next power. So this is already at power 1. So we raise it to the 2 power and divide by that 2. Right? So in this case, we just have to do that and then multiply by negative 61. So we get it was negative 61x, so we raised this to the, this is already the first power, so we raise it to the second power and divide by that. And then we keep this in there, and that will do it. Now if we take the derivative of this, the 2 comes here, this goes out, cancels with the 2, we get this times that. Right? So, okay, so that's the rule. So if so the question would be this, right? What is the antiderivative? Okay? And the answer is this. Okay? Is that clear? Okay, so we have this pretty simple idea of antiderivative, right? Just the opposite of derivative. It's just this weird notation, that's the only thing. Okay? So, now why do they have this weird notation? So why do they have that weird notation? Because the original problem had nothing to do with antiderivatives. The original problem is, suppose I want to know, suppose I write this. Now, what's the answer to this? Sorry, let's do this one. Yeah. Okay, what's the answer to this? Right? And then we said we could put a c here because we want to take the derivative of this and have it that, but if we have the c in there, you're taking the derivative of c, that's 0, so that won't affect it. Okay? So anyway, but let's not worry about that. Okay, so, but why do we have this crazy notation? Because the original problem is this problem. We're working with the function x squared, but the question has nothing to do with antiderivative originally. The question is, what is the area in between, say, 0 and 3, underneath that curve? Okay, now, that doesn't seem like an easy question, right? Right? How could we get that? So what is the height of this point? When x equals 3, y equals 9, right? Well, this point is 3, 9, right? Okay, so, the question is, what is this area in there? Which doesn't seem like there's any way to know. Right, this area here. Right? Okay, that seems pretty hard. That seems hard in the same way that if I gave you a function like this, or let's say, okay, let's use the same function, and I asked you, say at 2, what's the slope? That's also a hard question, right? If you just come at that raw, how would you answer that? Right? That's a very hard question. Now, we spent 5 weeks at least learning the answer, but if we didn't do that, it would be kind of no one would know how to do it. So this is in the same way, this is also hard to do, right? Now, can you make any estimate of the answer? Like, can you say, oh, it has to be less than something? Well, you could do this, right? You could draw a triangle like this, and say it has to be less than the area of the triangle, which is what, by the way? 1/2 the base times the height, right? What is that? 1/2, right? 1/2, 3 times 9, right? So whatever that is, 27/2. But at least it's less than that. But that's not exactly a good enough answer. Okay? So it's not easy, right? Okay? But the idea, I guess whoever was doing this, and maybe the people before them, they were working with the idea of approximating the answer. And they also had the tool kind of the limit. So just like when we tried to find the slope of this line, we approximated it by this, and then by this, the slope of this line, then this line, and so on. Right? We took the limit. That's what we did. That's how we got the answer before. Okay? So we did approximations